Hello friends. Today we will discuss maximum modulus principle. Maximum modulus principle. Now we know that what is meant by maximum modulus. We know that what is meant by modulus. If z is a complex number, then this type of concept mod z is called modulus of z, and this is nothing but square root of x square plus y square. Now we want to study this modulus and its maximality. And it's a maximality means when any number will be maximum or when any function will be maximum in its modulus. Maximum in its modulus, in terms of its modulus. That we want to see. Okay. So first of all, we will go for maximum modulus principle. We know that what is meant by maximum value. We know that maximum value of f of x is nothing but it is such a value. So we say that like this. We say that f of x has a maximum at some x equal to a if f of x less than or equal to f of a where a belongs to some number. So if this condition is satisfied, then we say that function is maximum at x equal to a, because all other values of f of x are less than or equal to f of a. This is the concept of maximum value. When we say that function is minimum at a if f of x greater than or equal to f of a, all other values at x which are different from a are larger or equal to f of a. So if f of x less than or equal to f of a in real analysis, then we say that f has maximum at x equal to a. And if f of x greater than or equal to f of a for all x, then we say that f has minimum value at x equal to a. At x equal to a. This is the concept. And this concept we want to extend for complex also. Complex valued functions. Let D be a subset of C. C is a complex plane. We are taking any subset. A complex function defined on D is said to have a local maximum modulus at A belongs to D if there exists a delta greater than 0 such that the disk having center at A and radius delta contained in D and mod f of z less than or equal to mod f of A for all z belongs to that disk having center at A and radius delta. Suppose our C is a complex plane. We have taken D is any subset of C. Suppose D is any subset of C. Okay, I will take this as D. So function, a complex function f is defined on this D. It is said to have a local maximum modulus at A belongs to D. We say that any function f which is defined on this set D has a maximum modulus at A belongs to D. A belongs to D. Suppose A is here point. A belongs to D. If there exists a delta greater than 0 such that disk having center at A and radius delta must be contained in D. It should be a subset of D or contained in D, and mod of f of z, modulus of f of z should be less than or equal to modulus of f at z equal to a for all z belongs to this D. So if I take any z, suppose I have taken z and I obtain value of z, f of z and then modulus of f of z. This is z1. If I take some here z2 belongs to this disk, then mod f of z2 also less than or equal to mod f of a. If such condition satisfied for every z in this disk, so the value of f at every z in this disk, modulus, the modulus value of f at every point in this disk, if it is less than or equal to the modulus value of f at z equal to a, then we say that f has a maximum modulus at z equal to a, which is same as that real analysis concept. That means in simple, we are saying that the modulus value of f at z equal to a is larger or equal to, means not less than, the modulus value of f at all other points in this disk, then we say that f has a local maximum, isn't it? F has a local maximum at a belongs to D. We have taken a here anywhere. So if your point is a here also, then we can also, there should be exist a delta. There exists a delta, isn't it? And a disk having center at a and radius delta. And if mod of f of z, where z is in this disk, is less than or equal to mod of f of a, then we say that f has a local maximum at z. F has a local maximum modulus at z equal to a. F has a local maximum modulus at z equal to a. Similarly, local minimum modulus will be there. What will be changed? If mod of f of z is greater than or equal to mod of f of a for all values of z in this same disk, then we say that f has a local minimum modulus at a belongs to d. This is the only. If the condition is reverse, then the concept is of minimum modulus. Concept will be of minimum modulus. So this is about what is meant by maximum modulus at a point and what is meant by local minimum modulus at a point. Okay, in simple, the modulus value of f at all other points except a will be less than or equal to modulus value of f at z equal to a. If this holds, then we say that f has a maximum local maximum modulus at z equal to a. And reversely, f has a local minimum modulus at z equal to a. That is the case. For example, on the closed disk mod z less than or equal to r, we have taken a disk such that mod z less than or equal to r. Means what? This is the circle having center at origin and radius r, and it is disk, no doubt. Okay, so consider this is the disk having center at origin and radius r. So this means all these points inside this. So suppose it is a disk, closed disk, mod z less than or equal to r. We have mod of e to the power z, means f of z. So let f of z equal to e to the power z. Suppose that f of z equal to e to the power z. So mod of f of z equal to mod of e to the power z equal to mod of e to the power x plus iy. We know that it is equal to mod of e to the power x into e to the power iy. That is mod of e to the power x into e to the mod of e to the power iy. But mod of e to the power iy is always equal to 1. Why? We know that e to the power iy means cos y plus I sin y, and its mod cos y plus I sin y, and its modulus is square root of cos square y plus sin square y, which is equal to 1. So this is nothing but only mod of e to the power x. X is real part of z, that is mod of e to the power real part of z. And what is real part of z? If you are, so it should be less than or equal to e to the power r, since because r is what? Mod of z is less than or equal to r. Mod z is what? Less than or equal to r. So real part of z is always less than or equal to mod z, and mod z is what? Here less than or equal to r. Mod z. So real part of z less than or equal to r. Therefore, e to the power real part of z will be less than or equal to e to the power r. So we got the local maximum value of f of z, right? Which is what? E to the power r. E to the power r. That means it is at z equal to r. It is at z equal to r. It is at z equal to r. So at the boundary, r means what? It is a boundary of this circle. So what we are saying, this function e to the power z has a maximum modulus at the boundary of this disk. Has a maximum modulus at the boundary of this disk. So at the boundary point z equal to r, e to the power z will be e to the power r. Thus e to the power z attains its maximum modulus at z equal to r. Similarly, now maximum value of r comma e to the power z means what? Maximum value of e to the power z at r equal to. On the other hand, here we proved The maximum value of e to the power z lies in the boundary of this circle, lies on the boundary of this. On the other hand, we will find maximum value of e to the power z at z equal to r. Does it e to the power r? That we want to verify, which is equal to maximum value for all mod z less than or equal to r of mod of e to the power z. And we know that it is equal to what? Again e to the power r. Again e to the power r. Similarly, for mod z less than or equal to r, we also have mod of cos z. We'll find the value of mod of cos z for mod z less than or equal to r. We obtain the value of mod of e to the power z for mod z less than or equal to r, and the maximum value is e to the power r. Now we will find the maximum value of modulus of cos z, where mod z less than or equal to r, this disk on this disk, which is equal to, we know that cos z is e to the power iz plus e to the power minus iz divided by 2, which is less than or equal to mod of e to the power iz plus mod of e to the power minus iz. Mod a plus b can be written as mod z1 plus z2, triangle inequality for complex number we consider, we use. Now mod of e to the power iz means what? E to the power iz is nothing but e to the power I into x plus iy, which is equal to e to the power ix minus I square y. Now plus I square y. I square is minus 1. So we get e to the power ix minus y. And if we have a modulus of this, then we get mod of e to the power ix into mod of e to the power minus y. But mod of e to the power ix is 1 again by using this one. And so we get only mod of e to the power minus y. Now e is always positive. So e to the power minus y is always positive. Therefore, we get only e to the power minus y plus e to the power, now here you will get y only. Okay, minus I is there because it becomes minus I square in this case, and e to the power minus ix modulus of e to the power minus ix is also say 1, and only mod of e to the power y is e to the power y. Now, so this less than or equal to e to the power r plus e to the power minus r divided by 2. Why? Because y, what is y? Y is imaginary part of z. Like real part of z, always less than or equal to mod z, which is less than or equal to r. Similarly, imaginary part of z is also less than or equal to mod z, is less than or equal to r, is less than or equal to r. That we have used. Therefore, e to the power y is less than or equal to e to the power r, and e to the power minus y is also e to the less than or equal to e to the power minus r divided by 2. You are getting divided by 2, which is equal to cos of IR. But this is for cos of IR. Cos IR is, what is cos x or cos z? E to the power iz plus e to the power minus iz divided by 2. Multiplying that by I, you will get e to the power r, means it is cos IR. Okay, it is cos IR. This is just formula. So what we obtain here? Mod of cos z is less than or equal to cos of IR. That means the local maximum value of modulus of cos z is at z equal to IR, is at cos of, or is at z equal to IR. That can be written. Similarly, maximum value of cos z, this implies maximum value of cos z with mod z less than or equal to r is equal to cos IR, but cos IR is again nothing but cos HR, because these two are same. Cos hyperbolic r is e to the power r plus e to the power minus r divided by r. What is sin HR? E to the power r minus e to the power minus r divided by 2. Okay, that is the cos and sin, and which is also same as cos IR. Though in real analysis, many functions such as cos x, sin x are bounded on R, in complex analysis, sin z and cos z are unbounded in C, because as your z is in C complex plane, your this R will be infinity. Modulus of z will be larger and larger at it is in complex plane, So R will be tends to infinity. As R tends to infinity, this will be tends to infinity again. And therefore modulus of cos Z will tends to infinity. That is, the function is unbounded. Similarly for sin Z. So mod of sin Z becomes mod of e to the power iz minus e to the power minus iz divided by 2i, which can be written in this way, which can be written in this way, which can be written in this way. Okay, it is like that, right? So it is minus only, therefore we get sin IR. To prove the maximum modulus principle, we need the following theorem from real analysis. What this theorem says that let h of theta be a continuous real valued function on AB with h of theta greater than or equal to 0 for all theta belongs to closed interval AB. And if integral from A to B, this is non-negative. Greater than or equal to 0 means what? Non-negative. So if integral from A to B, h of theta d theta is always equal to 0, then your h of theta should be equal to 0 for all theta belongs to in closed interval A comma B. This is the already result which we have proved in real analysis. What things we have taken in? Now note that if definite integral is 0, then this should be constant function. It should be constant function, obviously. But if that constant function is continuous on real valued function and non-negative, then it is not only constant, but it is zero function. But it is zero function. That already we have proved in real analysis. Now we have the proof of this also. We will prove it because already its a proof is in real analysis. Suppose we take any t belongs to AB. Therefore, 0 less than or equal to h of t. And how h of t we have defined? It is integral from a to t, h of theta d theta. As h of theta is non-negative for all theta belongs to AB, integral from a to b, h of theta is also non-negative, right? Because this upper limit is larger. Smallest value is a, largest value is b there. So this is a lower limit and this is the upper limit. So upper limit, as this is non-negative and upper limit is larger, so this should be non-negative term, whole should be non-negative, which is less than or equal to integral from a to b. If I take an upper limit higher than that, will be less than or equal to h of theta d theta, and we are given that it is equal to 0. So what we obtain? 0 less than or equal to this h of theta, and this is less than or equal to 0. Okay. So what we obtain 0 less than or equal to h of t less than or equal to 0. This implies ht equal to 0 on this AB. ht equal to 0 on this closed interval AB. That is h dash of theta is equal to 0 for theta belongs to AB. T belongs to, you can say that AB. H dash theta equal to 0 means what? What about h dash theta? If h of t is this one, then h dash of theta will be only small h theta. So small h theta, it must be 0 for all theta belongs to A. So if h theta is non-negative and continuous real valued function, and if integral from A to B h theta with respect to theta is 0, then that h theta should be 0 function. Now we will go for maximum modulus principle. Suppose that f is analytic in a domain D and A is a point in D such that mod f of z less than or equal to mod f of A holds for all z in D or z in D, not only in some disk. For all z in D it satisfies. Then f is constant. Then our f is constant. This is called maximum modulus principle. Means what? If a function f has a local maximum at z equal to A, if a function f has a maximum value at z equal to A for all z in D, then f should be constant. Then f should be constant. Suppose we have taken D is this set, and what we are saying, this condition is satisfied where A belongs to D. If I take any point A in D, then f of z less than or equal to modulus of f of z less than or equal to modulus of f of A holds, then f should be a constant function. Then f should be a constant. We have not taken this here, right? This is not there for all. So if f of z less than or equal to mod of f of A for all z in this D, then we say that f is constant. Then and then only f becomes constant. Means if f is not constant, then this will not be there. Okay, this will not be there. proof. Since A is in D, D is open because already D is the domain is connected and open set. And if A is in D, it is open and D is open. There exists an R such that a closed disk having center A and radius R must be in D. As this D is your open set and A belongs to D, we can find a delta such that we can find a disk having some radius R which is contained in D. Then F is analytic inside and on the circle gamma, which is the boundary of this disk having center at A and radius R. So as we have given, F is analytic in whole D. So if I take in that D a disk, then we say that F is analytic on disk as well as inside disk, and only boundary we have taken. So F is analytic on this circle gamma, which is the boundary of this disk whose center is at A and radius R. So by the Cauchy's integral formula, F of A is, if this holds, we know that by the Cauchy's integral formula, F of A equal to 1 by 2 pi I integral over gamma F of xi upon xi minus A dz, or this can be written as F of z upon z minus A dz, no doubt, no problem, both is same, which is equal to 1 upon 2 pi I integral from 0 to 2 pi F of A plus R e to the power I theta. What we have taken? Xi is equal to, we have taken A plus R e to the power I theta. So why? Because it is a circle having center at A, radius R, and this is that. So F of A plus R e to the power I theta, right? Xi is your A plus R e to the power I theta. Therefore, xi minus A is R e to the power I theta. It's F of A plus R e to the power I theta into derivative of this term with respect to theta, which is I R e to the power I theta d theta, which is equal to 1 by 2 pi I cancel. So we get 1 by 2 pi integral from 0 to 2 pi F of A plus R e to the power I theta d theta, because R e to the power I theta cancels with R e to the power I theta. So F of A will be this one. Now by the hypothesis, modulus of F of Z is less than or equal to modulus of F of A for all Z in D. So by hypothesis, mod of F of A plus R e to the power I theta, this complex number, is equal to mod of F of Z, and this is less than or equal to mod F of A. And by 1, we note that, now see here, but what is F of A? F of A is 1 by 2 pi integral from 0 to 2 pi F of A plus R e to the power I theta d theta. So mod F of A, which is less than or equal to 1 upon 2 pi integral from 0 to 2 pi mod of F of A plus R e to the power I theta into d theta, which is less than or equal to 1 by 2 pi 0 to 2 pi, because mod of F of A plus R e to the power I theta is less than or equal to mod of F of A into d theta. Now this mod F of A can be taken outside, only we get mod F of A upon 2 pi integral from 0 to 2 pi d theta, which is theta from 0 to 2 pi, so we get 2 pi. 2 pi cancels with 2 pi, only we get mod of F of A. So what we obtain? Mod of F of A less than or equal to this term, which is less than or equal to this, but which is F of A. So this whole term 1 by 2 pi integral from 0 to 2 pi mod of F of A plus R e to the power I theta into d theta is lies between mod F of A and mod F of A. That means this should be equal to mod of F of A. Okay. Therefore, 1 by 2 pi 0 to 2 pi into mod of F of A minus mod of F of A plus R e to the power I theta with respect to theta can be written as 1 by 2 pi first integral minus 1 by 2 pi second integral. But 1 by 2 pi 0 to 2 pi mod F of A d theta, 1 by 2 pi 0 to 2 pi mod F of A d theta, what is it? Mod of F of A, and 1 by 2 pi 0 to 2 pi mod of F of A plus R e to the power I theta lies between mod F of A and mod F of A. So this also equal to mod F of A. So this mod F of A minus sign, you will get 0. So this term you will get 0. Since the integral 2 is continuous and non-negative, so that mod of F of A plus R e to the power I theta must be equal to mod of f of a for theta lies between 0 to 2 pi. Why we have written this? So as this is non-negative, right? Because mod of f of a plus r e to the power I theta less than or equal to mod of f of a. So this is the largest value. As it is largest value, this difference is greater than or equal to 0. So difference is greater than or equal to 0 and integral equal to 0. So by that above result, this should be 0 for all theta belongs to 0 to 2 pi. So this should be 0 means these two should be same, equal. So mod of f of a plus r e to the power I theta must be same as mod of f of a for theta lies between 0 to 2 pi. This equation holds on all circles mod I minus a is equal to some s, which is less than or equal to r. That means if I taken a smaller circle, then also it holds. Again a smaller circle, then also it holds. So in every such circle it holds. And therefore mod fz is constant. So as this holds for f at modulus of f of a is same as modulus of f of z, both are same. So that means mod of f of z is constant on delta. That means a disk having center A, radius R. And therefore, if modulus of f of z is constant on this one, then fz should be constant by using a uniqueness theorem on whole D. So it should be a constant function. So we proved that if f is analytic in a domain D and mod fz is less than or equal to mod f of a for all z in D and a in D, then f is constant. So this is called maximum modulus principle. Now in maximum modulus principle, it is not necessary hold for open sets. Maximum modulus principle does not necessarily hold for open set. It is not necessary for open set. Further, this principle can be proved without using the theorem for real calculus. Theorem for real calculus, that is the remark. And this is the proof of that remark. So we don't want, but you only keep in mind that open set is not necessarily hold. Also, we can use one more way to prove the maximum modulus principle. Okay, this is one more one. If f is analytic in this disk, then we say that a free analytic function can be expressed in terms of its power series expansion about z equal to a that we have taken. In particular, for each circle mod z minus a equal to s with s less than or equal to r and positive, we have f of a plus s e to the power I theta. This is also in power series expansion we can write s to the power n e to the power I n theta for n greater than or equal to 0. Okay, now as mod of f of a plus s e to the power I theta, we have given this is less than or equal to mod of f of a, which is equal to a0 because it will be only a0. Okay, mod of a0 because mod of f of a means what? By putting s is equal to 0, you are getting mod of f of a. So all other terms you will get 0. Only s to the power 0 means first term will be there, that is mod of a0. And we see that mod of f of a plus s e to the power I theta square less than or equal to mod a0 square, which gives n greater than or equal to 0 mod of n square s to the power 2n equal to 1 by 2 pi integral from 0 to 2 pi f of a plus s e to the power I theta into, this is the square, z into z bar is mod z square that we have taken, less than or equal to 1 by 2 pi 0 to 2 pi a0 square d theta, which is equal to a0 square. And so an should be equal to, so summation over all n mod an square s to the power 2n is less than or equal to mod of a0 square. That is an should be 0 for each n belongs to natural number. Thus f of z equal to a0 on every circle. This one having center at psi and radius, having center at a and radius r. And consequently f of z equal to a0, that is f of a means what? It is a constant function on whole D. Suppose a function we consider f of a z equal to e to the power z for z in the disk having center at a, radius r, then maximum over circle having center at a radius r of e to the power z is equal to maximum over theta lies between 0 to 2 pi e to the power a plus r e to the power I theta equal to maximum of e to the power a, just separate. But e to the power r e to the power I theta is e to the power a means what? It is real part of a is real number, real part of a plus this is r. And the maximum modulus of e to the power z is attained at the boundary point z equal to a plus r. Z equal to a plus r. As in the previous example, this is very easy. Suppose we have given function g of z and we said that find the maximum modulus value of g of z. Write the maximum modulus value of g of z. Okay. So such type of examples may be asked in the examination. Find the maximum modulus value of g of z. Now let m is the maximum value of g of z for mod z less than or equal to a 1. So this is important. Mod z less than or equal to 1. Z cube plus 3z minus 1. Now consider z equal to e to the power I theta. R we have not taken because this is a circle having center, origin and radius 1. So R is 1 here. Let z equal to e to the power I theta so that mod of z square plus 3z minus 1 is equal to mod of z square is what? E to the power 2 I theta plus 3 times e to the power I theta minus 1. Take e to the power I theta common, you will get e to the power I theta plus 3 minus e to the power minus I theta. So modulus of these two separate means modulus of this is 1 again. So only we get mod of e to the power I theta plus 3 minus e to the power minus I theta, which is equal to e to the power I theta is what? Cos theta plus I sin theta plus 3 minus cos theta minus I sin theta. Minus I sin theta means that minus minus becomes plus I sin theta. Cos theta minus cos theta 0, I sin theta plus I sin theta 2 I sin theta. So we get 3 plus I into 2 sin theta. Now mod of this complex number is square root of 3 square means 9 plus square of this 2 sin theta square, that is 4 sin square, right? But we know that sin theta is, as theta is real number here, right? As theta is a real number and angle, since it is angle it should be a real number. Sin square theta always less than or equal to 1. Therefore this should be less than or equal to square root of 9 plus 4, that is square root of 13. So what we obtain here, mod of z square plus 3z minus 1 less than or equal to square root of 13 for mod z less than or equal to 1. In the disk mod z less than or equal to 1. So maximum value of modulus of z square plus 3z minus 1 in the circle mod z less than or equal to 1 is square root of 13. In this way we can obtain the maximum value of z. If I directly put mod z less than or equal to 1, then you get 1 plus 3 plus 1. You will get 5 only. And 5 is not the maximum value. That can be used, find by using this concept. So square root of 13 is the maximum modulus value of z square plus 3z minus 1 in which disk? In the disk mod z less than or equal to 1. So m equal to square root of 13 and the maximum value is obtained at where it is obtained? Z is equal to plus or minus I when theta is equal to plus or minus pi by 2. How we are writing? So maximum value is square root of 13 and where it will be obtained? Now when it will be obtained? If your theta is pi by 2. If your theta is pi by 2, square root of 13 plus or minus pi by 2. Z is equal to plus or minus I, that is theta is equal to pi by 2. Theta is equal to pi by 2. Okay, that is the case. Z square plus 3z minus 1. Z square plus 3z minus 1. Minus 2. Yes, why we are saying like that? See here. If I put z equal to plus or minus I, what will be z square? It will be I square. I square is minus 1 plus 3z. So I will take plus 3I and this as minus 1. So we get mod of minus 2 plus or minus 3I. And what is its modulus? Square root of 4 plus 9. It is what? Square root of 13. So it will be at z equal to plus or minus I, or at theta equal to plus or minus pi by 2. Because if your complex number is plus or minus I, then its argument is what? Plus or minus pi by 2. Plus or minus pi by 2. Where is that number? Here it is number. Plus or minus I. So argument is what? Plus or minus pi by 2. Here it is plus I and here it is minus I. So argument is plus 3 or minus. Now, so that is your maximum modulus principle. It is our maximum modulus principle. And now we will go for maximum modulus theorem. Maximum modulus theorem. Suppose that f is analytic in a bounded domain D and continuous on D bar, that is closed. Then mod f of z attains its maximum at some point on the boundary dou D of D. What this theorem saying? If f is analytic in a bounded domain D and continuous on its a closure, then modulus of f of z attains its maximum at some point on the boundary of that disk. So suppose D is this set, right? Any set is D, whatever it may be. Either we will take this as D or this as D. If f is analytic in a bounded domain D and that function is continuous on closure of D, boundary of D. Closure means this one is boundary. Then modulus, maximum value of modulus of f of z attains at some point on boundary. Some point on boundary. In between, it will not attain the maximum modulus value. Okay, that is the case. We know that a continuous function on a compact set attains a maximum. So by hypothesis, f is bounded on D bar, closure of D, and the maximum value of f, which is modulus of f of z, is attained at some point on D bar. By maximum modulus principle, it cannot be in D. Therefore, it must be on the boundary. Okay, it cannot be in D. Therefore, it must be on the boundary dou D of D. Why we are saying that by maximum modulus principle, it cannot be in D? What is the maximum modulus principle? This is our maximum modulus principle. Suppose f is analytic in a domain D and A is a point in D, such that mod f of z less than or equal to f of a, then f is constant. F should be constant. Means what? For every z, f of z is some fix, which is f of a, at the same as f of a, isn't it? So it should not be in the interior. It is everywhere. That is on the boundary also. For all z belongs to D. Okay, that is there. So it cannot be in D, therefore it must be at the boundary of TT. So what in small way, if your this domain is if function is analytic on this domain and also continuous on the boundary, then the maximum modulus value of f of z will attain on boundary, not in the interior. Not in the interior. Okay. Consider a function f of z equal to z square defined on the closed disk D, defined on the closed disk D, which is the set of all those points such that mod of z minus 1 minus I less than or equal to 1. Means what? What is it? It is a circular disk whose center is at 1 plus I and radius 1. Circular disk, center is at 1 plus I and radius 1. We show that the maximum value of mod f of z is attained at z equal to. We want to prove that this function has maximum value at z equal to 1 plus 1 by root 2 into 1 plus I. This is a complex number. At this point, we want to show that this f of z has a maximum value, maximum modulus value. Okay, where D is your what? Our D is what? This D is having center at 1 plus I and radius 1. This is our D. Okay, and we have to show that the f of z has maximum modulus at this point. That is 1 plus 1 by root 2 plus I into 1 plus 1 by root 2. Means whose x coordinate is also 1 plus 1 by root 2. Y coordinate is also 1 plus 1 by root 2. 1 plus 1. 1 plus I point means what? It is a 1 comma 1. Point is what? 1 comma 1. Center at 1 means x coordinate 1, y coordinate also 1 and radius 1. It is something like this. This is the point 1 comma 1. Radius is 1. Right? So this is disk is like this. Now 1 plus 1 by root 2 at 1 plus 1 by root 2. Okay, this is the point 1 plus 1 comma 1. Center is at 1 comma 1. Somewhere here 1 plus 1 by root 2 comma 1 plus 1 by root 2. It will be like this. Okay. For this set z equal to 1 plus I plus e to the power I theta. Z what we are taking? Consider z is equal to 1 plus I plus e to the power I theta, which is the circle. This is a plus r e to the power I theta. Every z having center at a and radius r, we express it as, in that case we said a plus r e to the power I theta. Now here center is a means 1 plus I, that's why we have taken 1 plus I. Radius is 1, so we have taken r is 1. Therefore we have said z is equal to 1 plus I plus e to the power I theta, which is equal to 1 plus I plus cos theta plus I sin theta. It is for this e to the power I theta. That is 1 plus cos theta plus I into 1 plus sin theta, for theta belongs to 0 to 2 pi. Then mod f of z equal to mod z square. Mod z square is mod of this square. That is mod of this square. So mod of this square means what? Only 1 plus cos theta square plus 1 plus sin theta square, which is equal to 1 plus 2 cos theta plus cos square theta, 1 plus 2 sin theta plus sin square theta. Right? So 1 plus 1 we get 2. 2 cos theta plus 2 sin theta, 2 into cos theta plus sin theta, and cos square theta plus sin square theta is again 1. So 1 plus 1 plus 1 we get 3 plus 2 times cos theta plus I sin theta. Therefore mod of f of z attains maximum at theta equal to pi by 4. Now we have to see that when this will be maximum. When this will be maximum, it is maximum at theta equal to pi by 4. In all other cases it will be smaller. How? If I take theta equal to pi by 4, we get cos pi by 4 is 1 by root 2, sin pi by 4 is 1 by root 2, 1 by root 2 plus 1 by root 2 is 2 by root 2, 2 by root 2 means only 2, that is 3 plus 2 root 2. That is 3 plus 2 root 2. Now, if I take theta is equal to pi by 2, then what will happen? One of them is 0. One of them is 0, and we get 3 plus 2 only, which is less than this one. So if I take theta other than pi by 4, every time this whole value will be less than or equal to that value, and therefore this will attain a maximum at theta equal to pi by 4, and therefore modulus f of z attains at theta equal to pi by 4, and the maximum value is 3 plus 2 root 2. 3 plus 2 root 2. That is, the maximum value is attained at z equal to 1 plus I plus e to the power I pi by 4 at theta equal to pi by 4. That is 1 plus I plus cos pi by 4 plus I sin pi by 4. That is 1 plus I plus 1 by root 2 plus I into 1 by root 2. So 1 by root 2 take common from this, we get 1 plus I. Then 1 plus I common from this, we get 1 by root 2 plus I times 1 by root 2. That is 1 plus 1 by root 2 into I plus 1. So that is at z equal to that one. Okay, it is like that. We have a corollary there. Suppose that f is analytic in a bounded domain D and continuous on closure of D, then each of real part of f z minus real part of f z, imaginary part of f z minus imaginary part of f z attains its maximum at some point on the boundary of this D. So everywhere, what we have proved, maximum value of f of z attains at some point on boundary. In the same way, not only maximum value of f of z, but maximum value of real part of f of z, minus of real part of f of z, imaginary part of f of z, minus of imaginary part of f of z, their maximum also lies on boundary. For this, we have considered u of xy is real part of f of z. Therefore, gz equal to e to the power f of z. Consider gz equal to e to the power f of z. By maximum modulus principle, mod of g of z will be mod of e to the power f of z equal to mod of e to the power real part of f of z, isn't it? We already proved it. Mod of e to the power x plus iy is equal to mod of e to the power x, which is real part of this one, and which is equal to e to the power u of xy. Cannot assume the maximum value in D because it will be in boundary of D. That is modulus of maximum value of modulus of g of z will be attained in the boundary. That means maximum value of, right, on the maximum value of this will lies on the boundary. That means maximum value of uxy also lies on the boundary, which is real part of f of z. Since e to the power u is maximized when u is maximized, we obtain that u of xy also cannot assume it's a maximum value in t. So in the same way, we can show that by, okay, for imaginary part of f of z, you will get same result. For minus of real part of f of z, we will same result. And for minus of imaginary part of f of z, also we get same result. Okay. So the maximum value of real part of f of z, imaginary part of f of z, minus of real part of f of z, minus of imaginary part of f of z will attain only on its boundary if it's attained, not inside the boundary. Okay, that is the case. These are simple corollaries are there, and some other examples are there which we have solved here. Okay, which we have solved there. Here we have obtained the maximum modulus value of cos z. Let d is a, actually it is not x, it is z. Set of all the z equal to x plus iy, where 0 is less than x and y is less than 2 pi. And in that case, we obtain the maximum modulus value of cos z. To do this, we first note that mod of cos z is equal to mod of cos of x plus iy. But cos of x plus iy is mod of cos x cos iy plus sin x sin iy. Sin x sin iy. And now cos x cos iy plus sin x sin iy. That means cos iy is cos hy. Sin iy is sin hy. I sin hy. That we obtain there. And then real and imaginary is cos square x cos h square sin square x sin h square. Converting cos h square y as 1 plus sin h square y, we get square root of sin h square y plus cos square y. So this is your maximum modulus value of cos z. Maximum modulus value of cos z. So by maximum modulus theorem, the maximum value is attained on the boundary of 2t, where we have taken here 0 is less than x comma y less than 2 pi. And what is the boundary? 2 pi is the boundary there. So that we have 2 pi comma 2 pi means 0 to 2 pi, 2 pi comma 2 pi, and 0 comma 2 pi, and then again. So maximum value lies on this circle, that we have proved here. Okay, that is the case. Similarly, second example, we have shown the maximum value of f of z equal to 1 minus z attains when z equal to minus 1. Z equal to minus 1, that is on the boundary of this. Mod z less than or equal to 1 is what? It is a circle having center origin radius 1. So on the left side also, z equal to minus 1 is the point on this boundary. Okay, that is the case. So it's a very, again, its calculations are there. So this is about maximum modulus principle. This is about maximum modulus principle. Okay, we'll see some other concepts in next lecture.